Hello, my name is Carly Franklin, and this is my submission for Lab 3, Circuits. The purpose of this lab was to use principles of energy conservation, Kirchhoff's loop rule, and in this lab it will predict the behavior of circuits containing resistors in series and in parallel, and then examining their behavior. And the principles used will be loop rule, node rule, Ohm's law, and resistor rules. So beginning with the procedure for this lab, I was instructed to create a circuit with 2 resistors and a battery and a couple ammeters to read the current. And I have my calculation shown on the right, and I got 0.02 amps to be my current, and my prediction was about right as shown by the simulation in the image. So reverse one of the connections to the ammeters. The reason that the reading is the same when it's backwards is because the ammeter is just measuring the magnitude of the voltage, and flipping the positive and negative terminals makes no difference. And then, as you can see, I recorded the delta V at each of those points on my circuit, and I got those numbers. And then the sum of the potential differences around the round trip should be equal to 0 due to Kirchhoff's loop rule, which relates to the conservation of energy in a circuit. And then my measured differences shown on the previous slide also add up to 0. And then here's my graph showing my potential differences. When I touch the voltmeter, the ammeter reading does not change because the voltmeter does not affect the current reading. No current is flowing through the voltmeter in the simulation. In real life, that might be a different story, but we're connecting the voltmeter across the 100 ohm resistor and then reading the current, and it's still 0.02. And then now, once we put the ammeter in parallel, as shown in the image attached to this slide, that is the only time that the current changes because the resistance is increasing and, the resistance is decreasing, and then the current is increasing as a result. And now part 2, RC circuit. We'll be using different resistors, which are going to be the bulbs, a 9-volt battery, and a 200 microfarad capacitor, and then we're going to just be playing around with that. And as you can see, I wrote down that the bulb lights up initially and then begins to dim and blow out due to decreased current. And then again, that happens when I disconnect the battery, connect the capacitor, and the bulb lights up again and then slowly dims out. So now for the comprehension questions. What happens to the current in the circuit as once the circuit is flowing? The capacitor is charging to its maximum Q, and so initially the current is at its maximum and then decreases over time because the capacitor is reaching its full charge, and soon no charge is flowing over it. And then once you remove the battery, then the capacitor discharges and the current begins to flow again. And then as you can see, here are my times to charge and discharge with 10 ohm bulb and 20 ohm bulb. And theoretically, these values should be the same when all else is held constant, but some human error is there with my time recording on my phone. And then now I was instructed to create a circuit and then plot my voltage versus time data. So here's just an image of my 2 circuits. Before and after I removed the battery, and the right image shows the circuit disconnected because at the end of the 20 seconds I quickly disconnected my circuit. Here's my plot, and on the left is what I used to create my graph on the right, and Excel was able to give me a helpful equation that I used on this slide. So just from Excel, working all that math out, my RC is equal to 6 seconds, but when I plug in my experimental data, I get 5.82 seconds. So the values are pretty much aligned, and the RC model accurately represents the circuit, but there's some human error there with why those values aren't the same. Discussion. If I was doing this lab in real life, and I used a real ammeter instead of a simulated ammeter, the real ammeter would have increased the circuit's resistance and then decreased the current, so charging and discharging would have taken a little longer. And then if I was doing this lab in real life and used a real battery, and there was no resistors in the circuit, there would still be an observable charging time, and I would still be able to observe current decreasing as the capacitor charges to its maximum. It would be, of course, a smaller amount of time because there is no resistor, but in my simulation, it says that my capacitor will reach full battery voltage instantly due to there being no resistance, and that is not what would happen in real life. And that is the end of my lab. Thank you so much for listening.